The first thing we're going to talk about, and your book really talks about this extensively, but I just want to highlight a couple points on this, is what is science? So, one of my favorite physicists is Richard Feynman. And if you ever have the chance to just sit down and search YouTube videos for Feynman, uh, you know, I highly recommend doing that. You'll find some, a very great, teacher and someone who can explain concepts much, much better than I can. But when asked, in his books, what he says science is the belief that the test of all knowledge is experiment. And I can't think of a better definition than that. So pretty much, if you want to look at what the scientific process is, it usually begins with somebody having some idea. So after they have that idea and a light bulb goes off in their head, if it's science, the first thing you have to do is try some experiment. Because it doesn't matter how clever you are, and it doesn't matter how good your idea is. Some of the most brilliant ideas that people have ever thought of have been completely and totally wrong. So you have to try an experiment to see if it works. And then, after your experiment, you ask yourself, does it hold? Because it might not. And in fact, most of the time it won't. So if not, you have to reformulate your idea. Or science books always like to call this your hypothesis, because scientists tend to like using big words sometimes. But that's all. So all that's really saying is, if your idea didn't hold, then we reform it, and then we do another experiment. Did that idea hold? No. Well, let's try and reform it again. We do another experiment. Sometimes you get so sick of this process that you just say, you know what, I'm just going to leave that idea alone and not worry about it anymore. But other times, it actually does hold, and you've come up with something new. And so that's when you publish it. You get to write a paper. It gets peer-reviewed by other scientists for them to say, yes, this idea works. This is something that someone hadn't thought of before. And so that's really cool. But then once it gets published, you're going to have this entire community of scientists. And scientists, by nature, are very skeptical people. So especially if you come up with something new, the first thing they're going to do is they're going to do more experiments. Because they want to know, first of all, they're going to try and recreate your experiment. Because if no one else can recreate it, then you have a problem. Then people are going to wonder whether or not the results that you gave are actually true. But for the most part, people are honest and they have real results. But people will try different experiments. People will do better experiments at a higher and higher precision. So when they do those experiments, they ask if it holds. And often, for a while, the answer keeps being yes. So, they do another experiment. Does it hold? Yes. And then they publish saying, yes, this idea still works. And they do some more experiments. Yes. But then eventually, with almost every theory, there comes a time when, after enough years and enough experiments and new technologies, we go back to a no again. All of a sudden, something doesn't work. And the reason for that is because most theories, in fact, almost all theories, are approximations. Oops. I will take this opportunity to tell you, you're going to see me misspell a lot of things in these videos, and if that bothers you, maybe you should find another series, because I have a tendency to misspell things a lot. But getting back onto, and I also have a tendency to ramble a lot like that, which I just did, and I'm continuing to do now. But so most theories are approximations. Almost every single theory is an approximation. And so eventually you're going to find an experiment that's going to invalidate the theory. And then because of that, you're going to have several different theories, and sometimes you're going to get paradoxes. That means you're going to have something, one common one that we have, and I believe that your book talks about, is quantum mechanics. Describes things that are very, very small, and to a very high level of precision. And general relativity describes things that are very, very heavy. And for the most part, things that are really small, the kind of small we're talking about, in quantum mechanics, which is like the size of, protons and even smaller, so even much smaller than atoms, is usually completely separate from the types of things we talk about in relativity, where we're talking about things with masses of like the sun, or larger than the sun, or, in smaller cases, even something like the Earth. But now, what happens if you have something that's really heavy and really small? Like the case that you have for something like a black hole, where you have something like the sun, and it's compressed down to like the size of a golf ball. So now you have things that are really heavy and really small. And all of a sudden, what we've found out is when you try to put the two together, we get paradoxes. We have, there seems to be conflicting results from both theories. And so in almost every branch of physics, the kind of the cutting edge, the state of the art, is reaching that very point where now your ideas and the theories of that field are starting to butt up against theories in another field, and somehow they have to be put together. But this whole process of coming up with an idea, and then doing an experiment, and then checking if it holds, reformulating, and doing more experiments and publishing, this is really what science is. So for something to be considered a science, it has to be able to have a process like this where you can actually test it and try and validate it and find out when it doesn't work, because there's almost always going to be cases where it doesn't work. And so that is science.